You are currently watching an artificial neural network learn. In this video, as we watch neural networks learn, you will learn how they learn. This is a continuation of my previous videos about neural networks as universal function approximators, and today I will finally explain the learning algorithm itself. And already there are 500 pedantic comments saying, it's not real learning because it's not conscious and it's just matrix multiplications and AI is neither A nor I. That sounds smart. Yeah, whatever, nerds.
Nobody cares.
By learning, I mean optimizing. We will compare two different optimization algorithms for neural networks, the state-of-the-art stochastic gradient descent, and for contrast, a simple evolutionary algorithm. We will watch real neural networks learn simple functions that let us visualize the actual training process in action. I will also be using a little interactive web toy that I made. You can play with this right now. It is a free and open source website. I hope to provide some insight for both newbies and experts, and show the similarities and differences, the advantages and disadvantages of these algorithms, and ultimately explain why one of them is the most optimized optimizer. Again, I recommend you watch my other neural network videos, but in short, functions are input-output machines, numbers in, numbers out. Neural networks are also functions and can reconstruct or approximate any other function to any degree of precision given only a sample of its data points. They are universal function approximators, and this makes them extremely general purpose for real-world tasks because
Functions describe the world.
Yes. The network shape as a function is defined by its set of parameters, the values of its weights and biases. Parameters are designed to be changeable, tunable, and different values produce different shapes. More parameters let you build more complex functions. With 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. This web toy has an extremely simple network with 2 parameters A and B, which we can control down here. The green line is the approximation, and the blue line is the target function and dataset. It's a sine wave. The neural network's actual function definition is here. It's using a tan-H activation. And as we change the values, we can see this green point moving around down here. This is parameter space, the space of all possible combinations of all possible values of A and B, between -5 and +5. It is a 2D plane, where the parameters are the coordinates, 2D for 2 params. Each point represents a different network, and collectively this is the space of all possible networks with this particular architecture, with 2 parameters wired up in this specific way. Note that this space would be very difficult to visualize if we had lots of parameters, like hundreds. This problem will haunt us throughout the video, but we will keep it simple for now. So, given a target function, it is clear that some of these parameters fit the target function better than others. We can search the space manually to find good ones, but how do we automatically find the best ones? This is the job of our optimization algorithm, which is fundamentally solving a search problem. It must search the space for the best set of parameters that produces the best approximation. In order to see which is best, we need a way to evaluate a network. Given a set of parameters, tell me how well a network with those parameters fits the target function. Remember that we don't actually know what the target function is, we only have a sample of data points. So let's take 3 data points from a sine wave. We can now give our network each input from the dataset and ask it to predict each output, and then compare the predicted outputs to the true outputs. We measure the difference between these 2 values using what's called a loss function. In this case, we will use mean squared error, but there are many other loss functions for different tasks. We calculate loss for all predicted versus true outputs, and then take the average across the entire dataset, which gives us a single final score for a given network. It's loss. Loss is a measure of error, so lower loss is better. We're playing golf here. Low loss means a small difference between predicted and true outputs, which means you have a good approximation. This big calculation can be generalized into a function, the loss landscape function, which takes a set of parameters as input and outputs the loss for those parameters on our current dataset. Now, remember parameter space? Using this function, we can visit every point in this space and calculate loss for every set of parameters, every network, and visualize the loss as the height of the plane at that point. This is the loss landscape. It tells us how good every possible network in this space is at approximating the target function. The green point represents our current network. The highest points are the worst networks, the lowest points are the best. We want the lowest. Mathematically, optimization simply means you are either minimizing or maximizing a function, or some kind of min-maxing, but we're not worrying about that in this video. For minimizing, you're trying to find the best inputs that produce the lowest output. We are trying to minimize the loss landscape function, whose inputs are parameters. The dataset values are not passed in as variables, but rather treated as constants, numbers hardwired into the function. They don't change no matter what your parameters are. This requires a conceptual rewiring of our neural network such that what were variables, dataset inputs, are now constants, and what were constants, parameters, are now variables. Thinking this way allows us to optimize input parameters to minimize output loss. We can now search parameter space using the loss landscape as our map. We can't just visually look at it and see that the lowest point is here, so these parameters make for the best network. Problem solved, we're done. Except, of course, in order to show this landscape, I have to generate and evaluate every possible variation of the network, in this space at least. With 2 parameters this is easy, but 2 parameters is nothing. Even on easy problems, a good approximation requires hundreds of parameters, which is both impossible to visualize and intractable to compute. You cannot realistically generate every possible combination of 100 parameters in a 100-dimensional hyperspace. And that is still very small for a neural network. With that many parameters, the loss landscape function can still be defined, and the loss for an individual point can be calculated, but the entire landscape can never be explicitly calculated in the way that we've done here. So our optimization algorithm must make do with this limitation. It must scale, even with absurdly high numbers of parameters. We've kept the dimensionality low so we can visualize it, but our algorithm must navigate the landscape blind. Imagine you are near the top of a mountain range. The landscape is rugged with many peaks and valleys. The air is cold and thin, and you must find your way down the mountain. But there's a hitch. You are blind.
I'm going to interview Eric Weihenmayer, who climbed the highest mountain in the world, Mount Everest. But he's blind. So we'll hear about that coming up.
Okay. That's you they're talking about. Blind and gay and stuck at the top of Lost Mountain. How do you find your way down? Well, one way you can try is to simply step in a random direction, and if you go down, commit to the step. Otherwise, do another random step. Better yet, take like 10 random steps and only commit to the best one. Repeat this over and over. This is the evolutionary way. Or you could just feel the slope of the ground under your feet and step in exactly the direction that it feels steepest downhill. That is the gradient descent way. Both are hill climbing optimization algorithms. Step by step, they climb down Lost Mountain, seeking the lowest point on the entire landscape, the global minimum. Let's start with the evolutionary way, random guessing and checking. We'll use an algorithm known as a local search, and it is just about the most bare-bones genetic algorithm that you could ask for. Start with a random network, a random point and parameter space, copy it, and mutate the copy's parameters by adding a small random value to all or some of them. This moves the point around a bit. Do this several times, so generate a population of candidate random steps. Calculate loss for all, and choose the one with the lowest loss for the next round. And repeat, repeat, repeat. Gradually, step by step, its descendants descend the mountain. The parameters are the genome of the neural network, and our loss function is the fitness function, or anti-fitness function. As biological life seeks the highest point on the fitness landscape, we seek the lowest point on the loss landscape. This website is actually performing a local search, which works pretty well on this problem. It can quickly find the lowest point on the landscape. We say it converges on the global minimum. It reaches a point where it just keeps getting closer and closer and closer. It is not guaranteed to converge on the global minimum. I will explain more about that in a bit. Either way, it finds the best approximation, but it still isn't a great approximation, and of course it's not. 2 parameters does not make for a very useful neural network. So let's switch over to a real PyTorch neural network and evolve it using a local search. This network has 1,741 parameters, so we can no longer observe the lost landscape directly, but we can observe the learned function. It mutates a random subset of parameters at a time, and you can actually see it adjusting them as it learns. The mutation rate gets smaller over time, so it can hopefully learn finer and finer details. I ran this for 150 rounds, each with a population of 1,000, so I had to generate 150,000 networks for this footage. That is a sacrifice I am willing to make. That's pretty good. Now let's try a more complex thing, an image. We'll use a smiley face. Refresher on how this works: the network takes the pixel coordinates as input and outputs a single pixel value, 2 inputs, 1 output. This image is made up of every output for every pixel. You treat every pixel in the target image as a data point in your dataset and approximate it. Every frame is a successful mutation, a strict improvement on the frame before. Loss can only go down or stay the same. This task is harder than the previous one. It takes a while, but it does eventually converge. Now, if we give it a proper image, like this picture of Mr. Darwin himself, we can see just how much it struggles to optimize. I had to tune the algorithm quite a bit to get it to perform even decently. The values that I tune, the population size, the number of rounds, the number of neurons, these values are called hyperparameters. They are not learned during training, but set beforehand. You can tune them by hand, as I have, or use a meta-optimization algorithm to find good hyperparameters. We're not doing that here. So it seems to have hit a wall. This may be due to the local search getting stuck in one of the many shallow valleys that are still high up on Lost Mountain. These are local minima, and they are where hill climbers go to die. Our local search cannot climb up and out, it can only go down. Loss always goes down. Likewise, real genetic fitness always goes up, and it too can get stuck on low hilltops. It can only make do with what it's got, it cannot go back to the drawing board. Our algorithm might be getting stuck in one of these local minima. But if you just keep running it, it does keep improving, very slowly. Gradualism, baby. We could improve this by keeping a diverse population of good candidates throughout the entire run, mixing their parameters with crossover mutations. We could be mutating the neural architecture itself and other hyperparameters along the way. I will explore these in a future video, but for now we must move on. A local search works pretty well if you have 1 billion years, but if you don't want to die before it converges, you will need something like gradient descent. Stochastic gradient descent, or SGD. Stochastic means it involves randomness, descent it's going down the hill, and the gradient is our secret weapon. The gradient is a vector, a list of numbers, each holding the slope of the corresponding parameter on Lost Mountain. If you have 2 parameters, you have 2 gradient values. Collectively, they make a line, seen here. Actually, that is the line tangent to the surface, which is not quite the same thing, but it includes the gradient. The gradient vector points in the direction of the steepest slope from the current position on the landscape. Give it a negative sign, and it points to the steepest slope downhill. The gradient is our compass on Lost Mountain. It is the slope of the ground that we can feel under our feet. Calculating it requires some calculus, multivariable calc. I've defined the lost landscape function a bit more generally here. We need to take its derivative with respect to each parameter, and we can do this because our lost landscape function is always well defined, even though our target function is unknown. So we start by using the derivative law known as use Wolfram alpha, and here's the derivatives. Go watch 3 Blue 1 Brown's video for the mathy math. There's a chain rule in there somewhere that gives us a partial derivative function for each parameter, which combined gives us our gradient vector. These functions tell us how loss changes as each parameter changes. This gets complicated for large neural networks, but it can be fully automated. Now we can calculate the gradient for any point and step directly towards the steepest downhill direction by simply subtracting the gradient from the parameters. Except that's probably too much, you will overshoot it. You want to scale the gradient down with a learning rate hyperparameter, something like 0.2. The gradient tells you the optimal direction, but not the optimal step size. You're still blind. You don't know what the function will look like in the next step. There are clever ways of choosing better step sizes, we'll talk more about that later. Just know that because the gradient tells you the best direction to step, there is no guessing and checking. This is a crucial advantage. We once again randomly initialize our network and evaluate loss with a forward pass. Then we go back throughout the entire network, calculate the gradient for each parameter, and apply the step, which moves the point. This is the backwards pass, aka backpropagation. And repeat. This results in a much smoother, more precise stepping algorithm than evolution. It is still a gradualistic hill climber, but more direct and less spazzy. Although it can get jumpy on steep slopes, it is not guaranteed to always reduce loss. The stochastic part comes from the random initialization, but also something called random batching. Rather than training on the entire dataset all at once, we train on small random subsets of the data called batches. We go through every batch in the dataset, taking a step for each, and then re-randomize the batches for the next pass. You can simulate this effect with simulate batching, which purely randomizes the data on every step. Because the landscape is defined by the dataset, it changes with every batch, but in the long run, these variations will average out to the same landscape. Mathematically, it is equivalent to train on the entire dataset all at once as it is to train on small random batches, though in practice, hyperparameters must be tuned. Batching is extremely useful because it allows us to spread out the expensive backpropagation algorithm over more compute time. So let's train a real network using SGD. This is using the exact same architecture as our local search, but this time with PyTorch's SGD optimizer. This works good. It is smoother than the local search and able to refine details to get a slightly lower loss. If we train it on an image, we can see that it is also smoother and really pretty. It looks like a candle. And be aware that this visual comparison is not scientific or fair, we're just eyeballing it, though SGD did take significantly less compute time to end up with a lower loss. But for the image of Darwin, we seem to run into a similar problem. It converges very slowly and not very well, actually worse than the local search. Again, we might be getting stuck in local minima, which are just as much of a problem for gradient descent as evolution. To help, we can add momentum to the final step, which helps it roll out of little gullies, but we've actually already been using momentum. A much more radical improvement comes from using a variant of SGD called Atom. Atom is basically momentum on steroids. It improves upon the final step size by using the first and second moments of the gradient. I won't explain more about Atom, but I will sing its praises. Atom rocks. It makes the training process way more efficient, way faster, and ultimately more capable. The final learned functions are much more precise. Hello, Mr. Darwin. Looking a little creepy today. Now remember that these are all generated with the exact same neural architecture, just with different parameter values discovered by different algorithms. There is another unintuitive way to escape local minima. Scale up. Add more parameters, which adds more dimensions to the lost landscape. What is a minimum in one dimension may be a maximum in another dimension. This is a saddle point, and it means that there is another way downhill. Research has shown that as you increase the dimensionality of parameter space, it becomes less and less common to find true local minima, where not a single parameter can be improved. On the hyperdimensional loss landscape, there is almost always another way down the mountain. Gradient descent is well poised to take advantage of this. The gradient will usually point to the optimal direction to escape the would-be local minima. Evolutionary algorithms can benefit from this, but they're not able to take full advantage. Because they must guess at parameters to mutate, i.e. directions to travel, they are precipitously less likely to guess the right direction as the number of directions grows. This is a more general problem with the evolutionary approach. As you scale up the number of parameters, parameter space grows exponentially. It becomes explosively unlikely that you will guess the right values to mutate. You will have to generate a lot of failed networks. However, note that it never becomes impossible, just very improbable. Given enough time, improvements will still accumulate. It just might take literally billions of years. We meet the curse of dimensionality again. It has killed many other optimization algorithms here too. The primary and unique advantage of gradient descent is scale. No matter how many parameters you have, you can always compute the gradient in linear time, and need take only one step in the optimal direction. This lets you take advantage of massive neural networks with billions of parameters without exploding the number of computations. It is the blessing of dimensionality, and it is why gradient descent is the state of the art. But this video is deeply unfair to evolutionary methods. I am comparing a heavily optimized gradient descent implementation with a homegrown dumb guy baby time local search. I will definitely make a follow-up video on the state-of-the-art evolutionary methods. I think there may be untapped advantages to algorithms other than gradient descent. The main limitation of gradient descent is that to calculate the gradient, it must be that the loss landscape function, the loss function, and the neural network itself are continuous and differentiable, or connected and smooth. No holes, no breaks, no gaps, no jagged edges, and no weird fractally bits that you can't differentiate. The gradients must flow. This applies to activation functions too, like the ReLU. This jagged point is not differentiable, but we'll just say its derivative is 1, and this works perfectly fine in practice. What are you going to do about it, math nerd? However, you cannot backprop through a binary step function like this, but you can evolve it. Pretty neat. And you can use it for images too, and make some really creepy looking smiley faces. You can't do this with gradient descent. It is possible to evolve very weird neural networks that are broken, jagged, or fractally that you can't train with gradient descent, and this might be useful. It's a neat idea, and it makes an interesting image, but this is not really a better approximation. There is a common view that evolution is just an inferior optimization algorithm, and, well, that is true to some extent. There's a reason we don't train language models with genetic algorithms. But I do think this view is missing something important. True biological evolution has something that none of these algorithms have, even the genetic ones. If you actually ran any of these programs for 1 billion years, you'd end up with just a better and better approximation. If you run true biological evolution for 1 billion years, you end up with eyes and wings and brains and pill bugs. Evolution diverges, not just converges. There's a lot more to say here, but alas, we're outside the scope of the video. Right now, gradient descent is the most optimized optimizer by far. It is the best tool for the job, and it scales, which turns out to be kind of a big deal. Large language models trained with gradient descent helped write the code and check the script for this video. It's cool that this algorithm can encode some weird understanding of itself into the very neurons that it trains. Don't worry, the script was human-written and human fact-checked too. I don't really like the way AI writes. And I always use human music. Check out my music guys, they're great. Okay, video's over. Get out of here.